Now let's look at energy conservation. What does energy conservation tell us about simple harmonic motion? We're going to look at a mass on a spring. So Hooke's law tells me that the force that the spring gives on the mass is equal to minus kx. Knowing the force will let me figure out how much energy gets stored in the spring. You see, suppose, let's remind ourselves how we figure out the amount of energy that gets stored in a system, in this case, a spring. What you want to do is imagine that I pull outwards. So this is the force from me. Let's call it F external. I can easily figure out how much work I do to stretch out the spring, and the work that I do, the energy that I gave out, is now stored in the spring itself. So to figure out the energy stored in the spring, let's call it the potential energy of the spring. What I have to do is figure out the work that I do to stretch the spring out by a certain distance. To do that, I have to integrate how hard I'm pulling dx. Work is force times distance, but with a spring, the force changes as I go, so I have to do an integral to figure out the work. Now, how hard do I have to pull? Well, I have to counter the pull of the spring. So I'm pulling to the right. Of course, the spring is pulling back just as hard to the left with a force minus kx. I'm pulling opposite that to stretch out the spring. So the force that I'm giving is minus the force of the spring. So the integral I have to do is minus the force of the spring dx. The minus sign here cancels out minus in the Hooke's law, so I have to do an integral of kx dx. And that's a very easy integral. It's 1/2 kx squared. Notice all the minus signs conspired to give me a positive result in the end. When I stretch the spring out a distance x, 1/2 kx squared is the energy stored. If I compress the spring in, it's the same way. It's not negative energy. If I compress the spring in, now I'm pushing, still opposing the spring. Both arrows in the picture just reverse if I'm pushing the spring inwards, and still positive energy is stored. So now we know how much potential energy there is stored inside of a spring. Now, the total energy is conserved. So even as our spring vibrates back and forth, or in this case, up and down, although at some moments there is no potential energy in the spring, that's when that's when the mass is actually moving the fastest. So there's a constant readjustment between the potential and the kinetic energy. When the potential is low, the kinetic is big, and vice versa. So it's a system which conserves energy. The total mechanical energy of the system is the sum of the kinetic energy plus the potential energy. That's 1/2 mv squared plus 1/2 kx squared, we just learned, is the potential energy. Now, the total amount actually stays constant. When the potential is low, because it's not stretched much, that's when the kinetic is big. So the total amount actually stays constant. What is the constant? In other words, what is the value of E? Well, it's easy to measure it because the energy, I could measure the energy at any moment. It's convenient to measure the energy when the spring is fully stretched out. That's when the mass has zero velocity, but it has the maximum stretch. So in other words, I could measure the energy when V is equal to 0 but x is equal to a. And so how much energy is there at that moment? Well, the v is gone, and I get 1/2. So that first term is 0. And I'm left with just 1/2 ka squared. In other words, the conservation of energy equation looks like this. Energy conservation for a mass on a spring looks this way. 1/2 ka squared is equal to 1/2 mv squared plus 1/2 ka squared. I meant x squared. Although from moment to moment, v and x change, the combined amount of kinetic and potential stays constant, 1/2 ka squared. Now, remember that previously I showed you in general. So this equation as it's written only makes sense for a spring. This is energy conservation for a spring, a mass spring system. However, in general, for simple harmonic motion, I showed you before that a squared is equal to x squared plus v over omega squared. And we argued that on general grounds just from the phasor diagram of simple harmonic motion. These two equations are really exactly the same thing. So, of course, there's a relationship between x squared and v squared because that's really what energy conservation is all about. If you have a spring system, then the value of k appears in here. But how would I recover this version of the equation? There's no spring constant in here at all. Well, remember that k over m is omega squared. So if I divide both sides of this equation, the spring equation, by k, I'll have m over k right here. And m over k is just exactly the same thing as dividing by omega squared. So the two equations are identical. This second version of it's really more useful because it's all simplified down. All you have to do is plug in the value of omega, and the use of it is if you know x and v at any moment, you can predict what the amplitude is. Sometimes you know the amplitude and you know the speed at some moment, and you're asked, well, what's the position? What is its position when it has a certain speed? And this equation is very useful for that. Now some more examples. This is just a child moving a plate back and forth in simple harmonic motion. Nothing to do with a spring, it's just a general type of simple harmonic motion. We know the mass of this plate and we know the amplitude of the motion. We're told that at a certain position from equilibrium of the motion, the speed of the plate is this. What's the period of the motion? Well, we know the amplitude. We know the at this position, the speed is this. How can I use that to figure out the period? Key is think back to that energy equation. A squared is equal to x squared plus v over omega squared. In this case, we're told the amplitude. I know at a certain position, the speed is 0.3 meters per second. It means I can solve for omega and therefore figure out what the period of the motion actually is. So the period, which is 2 pi over omega, we use the energy type of relationship to figure out omega, and then we can get the period to be 1.68 seconds. That's part A. Part B, what is the displacement when the speed is 0.16 meters per second? Notice that Sometimes you might be tempted to try to figure out at what time it has a certain speed and then go back to figure out the displacement. That will work. In other words, you could go back to sine omega t function, figure out the time when the speed is this, and then plug that time into cos omega t to figure out the position. It's a two-step process. It's faster, easier to use this energy type equation instead. So here, I want to know what's the position when the speed is this. I'm going to use exactly the same energy type equation. X squared is equal to a squared minus v over omega squared. We've already figured out the period now, and so we know the omega value, and we can plug in to solve for the position. Notice it's x squared equals something, so there are going to be two answers, of course. When does it have a certain speed? Well, on both sides of the equilibrium position. You see, when is it moving at 0.16 meters per second? Well, both when it's moving away from the equilibrium and then back towards equilibrium again. It'll have positive and it'll have two places where it has that same speed. Part C. In the center of the plate is a caret. The caret is just about to slip at the end point of the vibration. How strong must the static coefficient of friction be between the caret and the plate? So this is a review type problem. We got to remember back to in 221 what we've learned about static friction. What we know about static friction is that static friction can never be bigger than a certain value. At most, static friction at maximum is the static friction coefficient, US, multiplied by the normal force between the caret and the plate, which is just the weight of the caret in this case. M, that's the caret's mass. That's the 10-gram caret slice. That's M. Okay? So the friction force can never be bigger than that. On the other hand, it's that friction force which is pulling the caret along with the plate as it vibrates. You know, the caret's not attached to the kid's hand or something. It's that friction which is allowing the caret to move in simple harmonic motion. So that maximum force is also the mass of the caret multiplied by the max acceleration of the simple harmonic motion. That's Newton's law. So I can then figure out what the coefficient of friction is. I just have to know what the peak acceleration is during the simple harmonic motion. How would I do that? We have to remember that during simple harmonic motion, the max acceleration is just a times omega squared. And I know those values. It means I can solve for mu. If friction is the thing that's causing the acceleration of the caret, then I can actually solve for how strong the friction is. Notice the mass of the caret doesn't actually matter in the end. It cancels out on both sides. And mu comes out to be a omega squared. That's the peak acceleration compared with the value of g. The answer comes out to be 0.143. Next, we have a mass on a spring and it's hit like by a bullet. It sticks to the mass on the spring, and we want to figure out the frequency, amplitude, and period of the subsequent oscillation. So we have a mass attached to a spring. It's just happily sitting there at rest at the equilibrium position. But then like a bullet comes along at a given speed. Let's call that speed u. And it embeds itself in, and then it strikes it, and they move together, vibrating together. Could I find the amplitude of the motion by using energy conservation? In other words, could I set the kinetic energy of the bullet equal to the final energy of the oscillation? Is that true? Is energy conserved in an inelastic collision? The answer is no. This is inelastic. Think back to like way back when, Physics 130 or 221 or something. Energy is not conserved when things stick together in a collision. The energy is not conserved. However, the momentum is conserved. So this is a momentum conservation problem. Now, once it starts vibrating, then that vibrational energy is conserved. But energy from the bullet is lost in the collision. It goes into heat, basically. Now they rub together when they impact, and it's a bit warmer than it was. Okay, so we have to be super careful in this collision here. I got to use momentum conservation. It means that, let's call this thing M1, and this one's M2. It means that M1U is equal to the momentum they have just after the impact occurs. The momentum just after the impact is M1 plus M2 times V. I know the speed before the, I know the speed of the bullet. I need to know the speed that they have together after the impact, and then I'll know the energy of the vibration. So this lets me solve for the speed. The speed comes out to be 1.00 meters per second. In this case, it was so simple because M1 and 2 are actually equal. So after the collision, the mass is doubled, and therefore the speed drops by half. But it's a speed of 1 meter per second. Now that I know that, now I know everything there is now about the vibration that occurs. For example, I can now figure out the amplitude of the vibration. Now that I know the speed of the vibration, now I know the energy that they vibrate at. Notice after the impact, the energy is 1/2 times the total mass times v squared because they're stuck together. That is equal to 1/2 Ka squared. So now, after the collision, I can use energy conservation like I did here to figure out the amplitude of the motion, find the amplitude. The frequency of the vibration and the period, well, those just hinge on remembering that omega is the square root of k over m. K is the spring constant. The m value, you got to remember, is the total mass. The system after the impact is M1 and 2 stuck together and vibrating. So now you know omega, and you can find the frequency and the period. The period, for example, is 2 pi over omega. And this is all under part A. Part B, how long does it take the system to return the first time to the position it had immediately after the collision? That's not the period of the motion. Let's maybe look back at how the spring vibrates. The time to get back to where it started. So it was struck here in the middle. And how long does it take to get back to that point? That's only half of a cycle. That would be just this part of the motion right here, which is half of a period. So we're looking at t over 2 is our answer. From omega, you figure out the period, and half that is the time they're looking for.